This presentation is going to be about the biomechanics of running. We will cover 3 different biomechanical principles that can be seen while a person is running: ground reaction forces, the spring model of running, and drag. Ground reaction forces are the equal and opposite forces exerted on the body during contact with the ground. These forces are typically resolved into 3 components: vertical, anterior-posterior, and medial-lateral. They are best measured using a force plate. The vertical ground reaction forces have important implications in relation to running. Take, for example, the vertical GRF curve of a runner from initial contact of the foot to toe off. It can be seen that at its peak, the vertical ground reaction forces can be greater than 2 times the person's body weight. That's a lot of force being absorbed at the foot that needs to be distributed. As running speed increases, the peak vertical ground reaction forces increase linearly. Recent research suggests that the type of injuries a runner is prone to can be correlated with how the runner dissipates the forces, specifically looking at how they strike the ground with their foot. There are generally 2 classifications: rear foot strikers and midfoot strikers. Rear foot strikers tend to have a larger impact peak, while midfoot strikers tend to have a smaller impact peak or no impact peak at all. These peaks can tell us what injury a runner might be more likely to get. A larger impact peak means they are initially hitting the ground more forcefully and are more prone to bone tissue injuries such as stress fractures. A smaller impact peak means they are initially hitting the ground with less force and dissipating the loads more during mid-stance. This leaves them more prone to soft tissue injuries such as plantar fasciitis. The anterior-posterior ground reaction forces are also important when analyzing running. The first valley is called the braking peak, which refers to the deceleration of the foot as it contacts the ground. The force experienced at the braking peak is about 40% of the body weight in the negative direction. The second peak is called the propulsive peak. The propulsive peak is from the force generated during the acceleration of the foot off from the ground. The propulsive peak experiences about 40% of the body weight in the positive direction. When walking, the braking and propulsive peaks are about 20% of the body weight, or half of the force experienced during running. A typical anterior-posterior ground reaction force has symmetrical peaks. An asymmetrical anterior-posterior GRF indicates that the person is either accelerating or decelerating. If there's more area under the negative curve, they are decelerating, and if the positive curve is greater, they are accelerating. Medial lateral ground reaction forces produce the smallest forces out of the 3. The forces describe the inward roll, or pronation, of the foot from heel strike to toe off. Normal pronation is when, after heel strike, the foot rolls about 15 degrees inward through contact with the ground. Overpronation occurs when there is an inward roll of the foot greater than 15 degrees. This causes the majority of the forces to be applied to the medial side of the foot. Underpronation is when the angle is less than 15 degrees. This causes the majority of the forces to be applied to the lateral side of the foot. Corrective shoes with increased stability and control can be worn while running to minimize over and under pronation. Next, let's look at the spring model of running. To begin, it's important to understand the inverted pendulum model of walking. During walking, the kinetic and potential energies of the body trade off, allowing for a great deal of energy conservation. In the first half of stance, the body rises, increasing potential energy and decreasing kinetic energy. Subsequently, in the second half, the body falls and increases its kinetic energy by decreasing its potential energy. In this way, energy is highly conserved. Up to 95% is recovered in one stance phase. Running does not allow for the inverted pendulum model because the body falls in the first half of stance, decreasing both the potential and kinetic energies, and then rises in the second half, increasing both energies. The muscles therefore need to be performing more work than in walking. This is why it is more draining for us to run a certain distance than to walk it. The spring model describes how our bodies produce enough energy to keep us running. A spring, when compressed or stretched, stores elastic energy, which it then recycles when released from stretch or compression. Our tendons, muscles, and ligaments act as natural springs in our bodies. Specifically, in running, the Achilles tendon is a powerful spring that absorbs large amounts of energy during the first half of the stance phase and then recycles the energy to propel us forward in the second half. Finally, let's look at drag and how it affects running. Drag is a dynamic force that counteracts motion in a fluid. For running, the fluid is air. There are 3 types of drag: surface, pressure, and wave. While running, a person experiences surface drag, which only makes up about 3 to 5% of the drag force, and pressure drag, which makes up the remaining 95 to 97%. Since pressure drag dominates human motion, this is the drag we are going to focus on. Pressure drag is the front-to-back pressure differential. The side of the object with increased velocity will have decreased pressure, and the side of the object with decreased velocity will have increased pressure. Runners experience a drag coefficient of 0.9. A drag coefficient of 1 means that all of the fluid came to rest on the surface of the object, creating stagnation pressure or high pressure drag. The result of a high drag coefficient is turbulent flow, which means there is a non-uniform flow of fluid around the runner. Turbulent flow leads to a great front-to-back pressure differential. In comparison, a mackerel has a drag coefficient of 0.0053. This allows the fish to have laminar flow. The streamlined design of the mackerel reduces turbulence and pressure drag, thereby giving it a small front-to-back pressure differential. This equation is used to calculate pressure drag force, where Fd is the drag force, Cd is the coefficient of drag, P is the fluid density, A is the cross-sectional area of the object perpendicular to the relative velocity, and V is the relative velocity of the object with respect to the fluid. As you can see in the equation, decreasing the cross-sectional area will lead to less drag force. A person who practices good running form, which may reduce cross-sectional area, can become a more efficient runner. The equation also shows us that velocity is proportional to drag force. The faster a person runs, the bigger the penalty. And that concludes our presentation on the 3 biomechanic principles of running.